Ladies and gentlemen, it's my great pleasure to welcome you this evening. So our guest is Professor Jean-Pierre Lasota, the CNRS Emeritus Research Director of the Institut d'Astrophysique de Paris, and the Professor of the Nicolaus Copernicus Center of the Polish Academy of Sciences. Formerly the Director of Relativistic Astrophysics and Cosmology at the Paris Observatory, written 3 books and an astonishing, rather mind-boggling 250 articles, at least co-authored. And for some of these achievements awarded the Felix Robin Award of the French Physical Society. So we have here a scholar of truly vast distinction, whom it is a tremendous pleasure and no small honor to welcome this evening. And I'd just like you to join me in giving him a very warm welcome. Thank you.
I didn't realize it's going to be recorded, so maybe I will have to think how to change my talk. But thank you very much for inviting me, and it's a real pleasure to be here with you. And I also am happy to see that most of the people here are drinking wine, and you might need more during my talk, so please don't hesitate to go and take some more drinks, because I won't drink because I have water and it's sufficient for my purpose. Yeah. I hope it's water. Yeah, it is water. Okay, so the title, The End of Physics as We Know It, of course, I'm not sure what the we means, and we know it. So I will tell you about physics, how we in the general sense, and in particularly myself, knew it, and tell you what is happening now in physics, which is something very interesting. It's really new, it is worrying in many parts, and it's important to know because I think you will all agree that physics is the fundamental science. In fact, my next slide is what is physics. I'm not going to define physics. I'll just give you 2 quotations. One is by a great physicist, which says, all science is physics or stamp collection. And what is funny is that Edward got the Nobel Prize in chemistry. So he got probably for stamp collection. It is also interesting that many physicists got the Nobel Prize in chemistry. I'd never heard of a chemist getting a Nobel Prize in physics. And then there is a more sort of light quotation by the great Richard Feynman. Physics is like sex. Sure, it may give some practical results, but it's not why we do it. And in fact, this is typical of Feynman. He would like to be provocative, because he himself, of course, was not doing physics for practical reasons, but he contributed a lot to practical application of physics. And in fact, it is true that we don't do physics to apply it, but it almost always has some application. And for example, you probably don't realize that this GPS in this smartphone uses the general theory of relativity of Einstein. Without it, it would work. You also probably don't know that this laser, the principle of this laser, was also invented by Einstein. So, but he didn't look for practical application. He was trying to understand the fundamental law of physics. And if you think that, of course, Einstein, this absent-minded physicist, could not invent anything, you're wrong, because he had 2 patents, one for a refrigerator, and one is of personal interest to me, which is a hearing aid, which didn't work very well. It was too big, of course, in this time, but he was also an inventor. But he was not doing things, physics to invent things. So, in fact, the term physicist, the name physicist, the occupation of physicists is quite recent, and the word itself was invented by William Whewell, who coined the word scientist in 1833, and the word physicist only in 1840. It is more or less when this word was needed because the occupation of physicists was then becoming more frequent. Before, physicists were called philosophers, and physics was the philosophy of nature. And of course, the attitude of physicists towards philosophy has changed, and this is another quotation by Richard Feynman about philosophers. This is from his lectures. It's not something he said, you know, after a few drinks. He said, philosophers incidentally say a great deal about what is absolutely necessary for science, and it is always, so as far as one can see, rather naive and probably wrong. We will come back to the relation of physics to philosophy, but just before I tell you how physics has changed, let's go to the, let's say, the beginning of science, which was created, in fact, everybody would agree, by Galileo, who defined philosophy, which means physics or even science, comparing it to reading the book. The universe is a book we can read, but you have to know the language, and the language is mathematics. And it is mathematical language, which in his time was just geometry. He didn't know any different mathematics with triangles, circles, and other geometrical figures. But this was the first time that science was defined as a mathematical science. So it was physics is mathematics applied to the universe. And you are reading the law of the universe. The first and the greatest of ever physicists was Isaac Newton, who also discovered or found mathematics different from geometry. He is the creator with Leibniz of the differential calculus, but he also defined a method which is rather drastic, but he says that, I will just read the conclusion, that in experimental philosophy, which means experimental physics, particular propositions are inferred from the phenomena, not rendered general by induction. There's no hypothesis. You deduce everything from phenomena, which is rather drastic, and it has changed in during the evolution of physics. In fact, as you will see, it changed to the other extreme, which I will discuss at the end of my talk. But these two great men, Galileo and Newton, defined what physics is or has been until now. There was, of course, one problem, that if you infer things from phenomena, you have to, if you have to combine phenomena with mathematics, you have to make measurements. You have to describe the phenomena with formulae, with numbers, which needs to have precise measurements. And this was not so obvious. In fact, according to Freeman Dyson, modern science began in 1729, when it became based on measurements with high precision. The first high precision in the history of mankind was done by James Bradley, published, or in fact it was sent in a letter in 1729. And what Bradley measured was the effect on the position of stars due to the motion of the Earth around the Sun. It was the effect due to the speed of the Earth, and the apparent position of the star is not exactly where it is, where it should be, because there is a correction due to the speed of the motion of the Earth, and he was able to make a very precise very precise observation. He found the displacement is of the position is 20 arc second, which in the radians, which measures the size of the circle that the displacement takes, is given by this number. You see, it is very precise. It is was more precise than the previous measurement by a factor 100, and it goes to the six digit after the comma. So this was the first time that such a precise measurement was possible, and this was the possibility to measure, since we knew, I mean, he knew the speed of the Earth. This is the speed of light. This was the first precise measurement of the speed of light, and the first direct proof that Copernicus was right. It was the first direct measurement of the motion of the Earth around the Sun. Before then, it was just a hypothesis, if you apply Newton's reasoning. So this was the beginning of modern science, but in physics, one has to wait much longer to get this precision. In fact, physics became an experimental science more than 100 years after Bradley's precision, and Bradley's precision was reached in experimental physics only 200 years later. The reason was that it was very difficult to make precise measurement on Earth with normal matter. It's much easier to measure. It was very difficult, but it's much easier to measure the position of a star, of a celestial body on the sky. It is very difficult to measure something in the laboratory. And the best example was James Prescott Joule, who in 1845 measured the so-called equivalent, mechanical equivalent of heat. He was measuring how much heat is produced by mechanical work, and he was able to measure temperature to within 1 part in 200, which was unheard of. And in fact, he was not believed. He presented, his paper was rejected from publication. He presented his results and was met with silence because nobody could believe it. What is interesting, seeing that you drink wine, that Joule got this expertise by being a brewer. And apparently he was producing a very, very good beer because he was able to measure the temperature of the vat or whatever it was with such a high precision. But this was extremely difficult. You can see this is the scheme of the apparatus. This is the apparatus itself. It doesn't look very sort of scientific, but it was. So this was this conflict between the requirement of experimental science and the quality of the measurement of experiment. And it ended only recently, in fact. Recently, I mean, before I was born, but in the 30s, I would say, in the 40s, one got really the precise measurement of the same quality as Bradley's measurement in 1729. One sometimes forgets that the influence of industry, of real life onto physics, and there was an enormous influence of steam machines on the birth of modern physics. James Watt and other people built these steam machines, and physicists try to understand how they work, what their efficiency. And this was sort of a mixture of practical science and fundamental science. And in fact, it's through understanding the so-called, this is the schematic mathematical machine invented by Sadi Carnot, who described a cycle which was the beginning of thermodynamics, the description of the heat exchange, this heat structure of gases, of various bodies. It was the first time that physics was no longer mechanics, description of the motion of the bodies. It was description of an internal structure of the body. It was then that only then one understood what is energy, what is heat, what is entropy. I mean, it was not understood what is entropy. It was then introduced entropy. It was a completely new science that was created because of the need to explain the working of steam machines. On the other hand, there was probably the first break in Newton's idea that you don't make hypotheses. It was made by one of the greatest physicists, James Clerk Maxwell, who created electrodynamics. He unified magnetism and electricity, and in doing that, he found that there should exist electromagnetic waves. He understood that light is an electromagnetic wave, but he also predicted that there must exist many other forms of electromagnetic waves. And Heinrich Hertz, much later, built an emitter of, in this case, radio waves, and a detector. So it was first was the hypothesis, and then was the detection. And then I could not resist by quoting this. Heinrich Hertz made this probably the biggest understatement in the history, at least of science. He said, it's of no use of whatsoever. Radio waves will be never used. It was just an experiment that proves Maestro Maxwell was right. Okay, this is also a big illustration. We do physics not for practical applications. Even if you don't want, you will find always a practical application. Now, the tension is, now is we don't say conflict in physics, now we say tension. Probably it's more politically correct. You don't say that the two results are, this result is wrong because it's different from another. You say it's a tension between the two results. So the biggest tension between theory and experiment was during the 19th century when a kinetic theory of gases and statistical mechanics was developed by three great men, once more Maxwell, Ludwig Boltzmann, and Josiah Willard Gibbs. The idea was to understand the law of thermodynamics. What is heat? What is entropy? And this was based on the very old, ancient atomic hypothesis that gases are made of atoms, and what we described as a general property of a gas is in fact the result of properties of motion of atoms. This was met by violent opposition, really violent opposition, from various people. The most famous were Ernst Mach, the well-known philosopher, scientist, and Wilhelm Ostwald, who was a physical chemist. He was a personal friend of Boltzmann, but they were fighting to the point of, when you read how they were written, it's unbelievable. Just to claim that the atoms cannot be, should not be considered by physics because they will never be discovered. Even they were real, they are so tiny, you will never get to see atoms. So physics should not speak about atoms. It could be a useful mathematical tool, but it's not a real being. And people were really very, very, very violent about it. Even Max Planck, I was surprised to find, he was, at the end of the 19th century, still was skeptical about the existence of atoms, Max Planck. And this was only solved by a very unique combination of theory and experiment. There were known phenomena of Brownian motion. This was in a fluid. There was when you observe suspended pollen, you see that under the microscope. You see they are doing this type of motion. If you follow a pollen like here, you see they do such motion. This was described by Einstein and independently by Marian Smoluchowski as the result of many collisions of atoms or molecules. like it is described in this. This is a simulation. And Jean-Baptiste Perrin made a series of very precise experiments proving that the law discovered by Einstein and Smoluchowski found their application. They were tested by him in experiment. This ended the polemics about the existence of atoms, at least for Ostwald. Mach died still being skeptical. Ostwald said, okay, I give up, atoms exist. And he was right, because nowadays you can even catch atoms. This is a photo made not far from here in Oxford. And this is an ion trap. And this point here is one single atom. I mean, it's an ion, but it's an atom. So now you can catch atoms. The atoms that were supposed to be invisible forever. There's even more amazing things are happening. This is a film made by IBM in which you see single atoms. These are single atoms, as you will see. It's a very short movie. It's worth seeing because it's unbelievable. These are atoms, and then you can make them move with something which was scanning tunneling microscope. And this is just entertaining film, but this is so-called nanotechnology. In these 12 atoms, you can put one bit of information, and you see what you can do now with single atoms. I'm not going to. Okay, it could be more entertaining than my talk, and certainly shorter. But this is a play, but this is a way to construct very tiny, for example, computers. And okay, I will go to here. This was suggested years ago, in 1959, once more by Richard Feynman. He invented nano-physics and nanotechnology. And this is just a quotation from this article. He said, if I have written a code with 5 times 5 times, which is 125 atoms to a bit, he was a bit sort of modest, because now we have 12 atoms to a bit. Then he described how to improve electron microscope, and so it should be possible to see individual atoms. He was right in 59. Not only you can see, but you can play with them. You can even play soccer with them, sorry, football. And this nanotechnology was, as you probably know, maybe some of you, Michael Crichton even wrote a novel about, in 2002, about a sort of a science fiction about nanotechnology that apparently scares some very important people in this country. But I'm not going to give any names. So it is not scary, it is very useful. So today, now I make this jump from 19th century today. Today, physics allows us to understand the structure of matter on scales differing by 10 to the 18 orders of magnitude. We understand matter, what is, I mean, this type of matter. We understand crystals, atoms, atomic nucleus, nucleon. A nucleon is a proton or a neutron which makes the atomic nucleus. It is made, and then we understand what it's made of. It's made of so-called quarks. So we understand the structure of matter on an enormous scale. And if you add to that the radius of the observed universe, 10 to the 26 meters, you can say we understand 10 to the 44 scale. I mean, something which is 10 to the 44 smaller or larger. So this is really very impressive, and it is true. We have the so-called standard model of elementary particles. So we know that particles, the all matter we know is formed from so-called quarks. In fact, the matter we know is made only from these two quarks. There are also so-called leptons, which are the electron, neutrinos, and some more exotic particles. There is the Higgs boson that everybody heard of course. It was described and it was discovered recently, predicted much earlier. And we know particles that are responsible for forces, because forces are transmitted by particles. This is our old photon, the one that operates here and everything. And this describes the so-called weak interaction, and this is the so-called gluons that glue, you will see in a moment, next slide, that glue nuclear particles together. So we understand everything on this level. These are two types of particles, because in the universe there are only two types of particles, called fermions and bosons. I mean, boson, this is also a boson. We know, I'm not saying we know everything, but we understand most of these things. In fact, this is quite recent, a few years ago, but now we understand exactly what is the inner structure of a proton, which is the major constituent of a nucleus. And I'm not going to explain that, but it is a very complicated combination of three quarks, pairs of quarks and antiquarks that are glued by gluons, of course. We also have now extremely high precision of measurements. We are not longer the six digit, but we have now, this is the measurement, a recent 2006 measurement of the so-called magnetic moment of the electron, and you see this is part per trillion. So you see this was the error, so-called error, the uncertainty in 87. Now we have this very precise measurement, and also we can compare experiment with theory to the precision 10 to the minus 12, which is the most precise, or even 13, which is the most precise measurement in physics. And you should realize that it tests so-called quantum electrodynamics, which is a test also of special relativity. So there are still some people who try to revise with some simple experiment and say Einstein was wrong because I measured the distance and then I explained. The answer is, okay, explain this. So this is, and we are still going to improve it, because there's still this hope that maybe at some digits something will go wrong and there will be new, so-called new physics. We also have precision cosmology, for example. It's not at the same level. It's the level of 1%. But here we are measuring distances, very large distances in the universe, and the precision of 1% is already almost a miracle. And this diagram shows the evolution of the Hubble constant over the time, but it's not the physical evolution, it's the measurement. And there are three methods of measuring the Hubble constant. The Hubble constant is what measures the rate of the expansion of the universe. And you see there were big errors here, but now there are three methods of measurement that give different results, significantly different results. And this is what I mentioned, the word tension. This is what my colleagues who work on that call it tension between the three values of the Hubble constant. But this is what I mentioned just in my one of the previous sentences, is that more precise is the measurement, more is hope there will be some problem. In this case, I think there will be no problem. There will be some systematic error or something, but this is my personal view. But just we arrive now we are even better than was Bradley in the 17th century, in the 18th century. Okay, so, are physicists happy or unhappy? Because we have such fantastic precision. We know everything, as I said, so everybody should be happy. And it depends whom you talk to. There are two problems, two basic problems. They are probably related. One is that's why I put Einstein before, because Einstein has this dream to unify all the forces, or we prefer to say interaction, in the universe. So we have 4 types of interaction. Gravitation, that we know very well. Electromagnetism, we know also quite well. Weak interaction and strong interaction that are operating only at the level of an atomic nucleus. So we don't know them, but we depend on them. And they are different. They are different, described by different theories, by different equations. They have different properties. And Einstein had this dream that there's only one interaction that for some reason appears as being in 4 interactions. And so there is this dream of unification. I mean, the first, I put here electric and magnetic. This was done by Maxwell, but in fact, it's explained by special relativity. It was on the quantum level, the electrodynamics and the so-called weak force were unified, and so they correspond to this. This is a hypothesis that if you increase the energy, they will be unified at some level of energy which is debatable. But we know that it is unified here, and many physicists are unhappy, like Einstein was, that these forces are not unified. So this is one reason to be unhappy. Second is a physicist can ask a question, is we go to the quarks, is the quark really an elementary particle? Okay, we believe that atoms are elementary particles, then we believe that protons are elementary particles, then we found that they compose of quarks. And are they really elementary? And there is a very, very, oops, what I done? Okay. There is a very popular, I will come back to that, a theory, which is a mathematical theory, that claims that, in fact, everything is made of strings, little strings, really very little, because the scale is 10 to the minus 23 centimeters, which is 17 orders of magnitude smaller than the scale we have access to. So there would be very, very deep, so deep that there's no way of accessing it. And it's not like with atoms that people are saying we'll never see them. This, you can calculate how much energy you need, that, and there's the whole energy that you can produce on Earth would be possible to get to this level. In fact, you would have to get the energy that was produced in the Big Bang at the beginning of the universe to get to this level. But this is a source of real unhappiness, because you will see, because on the one hand side, you have a beautiful theory that says that such things exist, and then you have no way of accessing it. And there is something which comes from the observing of the universe, and some of my colleagues are very happy about that. I'm sorry, proud at least. They say the big success of our research is that we don't understand most of the universe. We don't know what it's made from. I was saying you should not be happy, you should be ashamed. Because we know that the matter we know and we understand, all these things that I said, we are proud, we understand everything. In fact, we understand only 4.9%. All the rest is supposed to be made, of dark matter. What's dark matter? We don't know. We try to find it, we don't find it. and so-called dark energy, which is not a good name, but it's used, which is even 68%, and we don't have the slightest idea what it is. There are some models, etc. So that is a real reason to be unhappy. Even if some of my colleagues, as I said, are very proud. And they spend a lot of time, a lot of money, proving that we don't understand most of the things we are observing. So there's another problem that is connected with that if we want to really understand, if we are unhappy about that, we have to use more and more energy on the level of elementary particles, and we should see close to the beginning of the universe. We should have bigger and bigger instruments and better detectors, etc., which implies so-called big science, which is very expensive. It is billions of pounds I put here because I'm speaking Oxford. Very large collaboration. I will illustrate it. Very big data, which now implies machine learning. Science is going to be done by machine. If you open the archive when people publish the preprints every morning, you can say now 20–30% of papers are about machine learning because there are so huge data with human beings are unable to do that. And soon we might have found a new word for the physicist who is a machine. I hope it's not going to happen. And something which you might find is not very important, and we have it, but it's a mistaken belief that we have powerful computers that can do everything. We need very fast, very powerful computers, and we don't have the computers we need. The computers and the software. And so to illustrate what I said, this is an example. It's a future circular collider called FCC. This is the present collider. This is an accelerator near Geneva. This is called LHC. This is the future. So it is 27 kilometers of diameter. This one is not of diameters of the legs. This is going to be 100 kilometers. It's going to get to 100 tera electron volts. It's a unit of energy compared to this one that was only 14. So this compares the circumferences. The problem is, in addition, that the cost is estimated between 9 and 21 billion euros, just, peanuts, as they say in Brussels. And maybe I shouldn't mention Brussels today. And then we come back to this unification of the forces. The unification was made at 0.1 tera electron volt, TeV. The FCC is going to get us somewhere here, but the real action is expected 9 orders of magnitude larger, or even more. So we are going to spend, say, 21 million, and knowing life is going to be 30 or 40 billion euros to find what? It's not clear. Okay, so some people are opposing that. Physicists, I'm not talking about, of course, about governments and ministers, etc. No, so physicists, why spend so much money on something we can't even predict? You're asking what's going to be. The LHC itself, we had already to discover so-called supersymmetric particles. Nothing happened. Okay, discovered the Higgs, great deal, but not what it was supposed to do. In fact, now we are not talking about that. So this is a big problem. It's not only money, it's only thousands of people that are supposed to work on something is not clear that will get a result. There's also a very bad example. This is astronomy, unfortunately, my main field. This is 6 meters space telescope. It is supposed to see the edge of the universe. It's going to be infrared because everything is shifted to the red. if it is far away, so it is the James Webb Space Telescope. The Planet launch was in 1997. It cost $500 million. It is supposed to, actually, I don't know, be launched in 2021, and the cost is almost 10 billion. Okay, and still is still in the lab. It's still not on the orbit. So there's also a risk. There's, I think, a big problem, which is problem maybe not of physicists, but it is because we are doing that we are not able now to run big projects. We don't have these big leaders that we had 20, 30 years ago, these horrible people sometimes, dictators, but they were able to make this big experiment. Now it is a lot of documents. It's become a big bureaucracy. And this is the result. You may say it's boring, it's not physics. It is part of physics. If you want to spend 20 billion, you have to know how to organize it, how to spend it. And it's not only a problem of physics, of course, but. And we have now, this is a publication of the LIGO Virgo collaboration, okay? You are laughing, I'm showing only small numbers. It's only, I think, 1,035 authors here. And just I put it in red, these three people are the Nobel Prize winner. So this is, it's not only a problem, it looks funny, or it looks a bit ridiculous, but most of the authors of this paper, they haven't read the paper, they don't understand the paper, because they were, technicians or something, they are not even interested. On the other hand, they are extremely bright people. I know many of them. Many young, very bright people, and they want recognition. You can't even recognize the Nobel Prize winner. So this is also a sociological problem, how to attract young, bright people to this very important project when they got lost in this crowd. There's a paper of the same collaboration plus another collaboration in which I counted the names and the addresses take 23 pages. Okay. This is, of course, an interesting evolution because it was an 83 paper, the famous paper of the CERN experiment that discovered the so-called intermediate boson, the bosons that the three bosons I've shown in one of my previous diagrams, and this probably is, I don't know, a few hundred, 200 or something. And this is also a Nobel Prize winner. It's not so lost. We are now, I want to show the importance of computers. We are now building an enormous, European extremely large telescope, ELT, 39-meter telescope, cost between 0.5 and 1 billion, so it's not so expensive compared to the other stuff. This is an artistic view. This is the mock. This is not the real mirror, but it is sort of made to show the size of the mirror. You see, it's not a uniform mirror. Each mirror is the mirror is composed of smaller mirrors. All that is going to be steered by a computer. The shape, the big 39-meter shape, is going to be steered by computers with so-called active and adaptive optics. This is just an example of the other side, of course, of the 1-meter mirror. And this is the scheme that shows there's a wet computers here. Without computers, you don't have these observations. It's impossible. And this computer has to be very fast. They have to adjust the shape of a 39-meter telescope in fractions of seconds. Another reason why we need huge computers are gravitational waves. You've seen the paper, one of the papers. This is the merger of two black holes. The precision of the measurement here is amazing. It's 1,000th of the size of a proton. To get that, you have to have fast and powerful computers which operate the detector. And to understand the result, we also have to calculate so-called templates. And some of the templates, the numerical calculation, can take up to 2 years with the fastest computers. So this is the end of experimental physics as we knew it. As an example, I show the detection of gravitational waves. This is Joe Weber in the 60s with his detector. And it was one scientist, in fact, few technicians. It cost with thousands of dollars. No computer were used for that. Today, we have thousands of scientists, billions of dollars, and huge computers. Okay, but don't laugh, because he hasn't discovered anything. And they are now discovering one merger, one signal of gravitational waves a week or every second day. This is the difference in, it was 50, 60 years it took to get, and the number of money and people that were working on that, to get a detection. So it's not a waste. It shows that it looks nice, and Joe Weber claimed that he detected something. Unfortunately, it was not true. So let's go to the other side, theoretical physics. Because as I mentioned, we want to know what is at the bottom. Not the bottom of Feynman, which was the atomic level. This was the real bottom, the end. And this is a vision that it is produced by the Superstring Theory. So, in fact, the universe is not what we know. This is only part of it, the 4-dimension, 3 spatial and time. There are some additional 5 to 6 dimension. But at each point, can you imagine like that, of the space-time, there is additional 6 dimension, but they are this called the compactified. They are curled at the size, and they have the size of the 10 to the minus 33 centimeters. So they are not detectable, but they are there. And there's also a vision of the universe in which you have so-called brains, membrane. You cut the mem and you put a number of dimensions, and you get a 2 brain or a p brain, and you have this vision of your universe on a brain. And you have closed strings and open strings. Oh, this is extremely beautiful, extremely complicated. This is a very advanced mathematics. Mathematically, it is perfect. It is a beautiful theory. The Pope of superstrings, Edward Witten, is the only physicist who got the Fields Medal for his work. So this is something incredibly beautiful. The only problem is you cannot test it. But it also inspires cosmology. So there is so-called ekpyrotic bouncing universe, when you have the universe. We are on a brain, and there's also another brain, and these brains collide, and then they separate, and this is sort of a eternal return. So the Big Bang is just one of the Big Bangs that were happening infinitely in the time and will continue to happen. So there is no real Big Bang as a beginning, because the beginning, the Big Bang, is just a collision of the two brains. So it's the end of the previous epoch. There is a competition, it's so-called the inflationary universe, that is based on a different idea that the universe, in a tiny, tiny fraction of a second, I mean tiny, tiny, tiny fraction, expanded for the size of the subatomic, let's say, to almost the present size, due to the action of a particle of a boson, which is called this inflation. So the name of the particle is inflaton, because we don't know if such particle exists. There's a speculation that the Higgs boson could be that. All this is extremely speculative. It is testable, but the situation is a bit strange. As an example, 3 years ago, in Scientific American, 3 scientists. These two are proponents of the ekpyrotic universe, published an article in Scientific American saying that the latest astrophysical measurements combined with theoretical problems cast doubts on the long-cherished inflationary theory of the early cosmos and suggest we need new ideas. Okay, it was in a popular journal. You would expect an answer, no, you are wrong because this and that. No, the answer was a manifesto, a letter of 33 very distinguished scientists, including 6 Nobel Prize winners, 1 Fields medalist, the Astronomy Royal, and Stephen Hawking. And they wrote, I'm not going to, you can read, but the main argument was that there are now more than 14,000 papers in scientific literature written by over 9,000 distinct scientists that use the word inflation or inflationary in their titles by claiming the inflationary cosmology lies outside the scientific method. The authors are dismissing the research of not only all the authors, etc. This is supposed to be an argument. Before 1905, every single and all physicists were believing and using the word ether. And then one clerk in a patent office wrote a paper, and the ether disappeared like that. So what is the argument? I mean, this is, where are we, what, I don't know what is happening. How can you discuss by using the number of papers, maybe the number of citations, and by extremely serious people? I don't know what is happening. As they say in French, le ridicule ne tue point. Ridicule haven't killed anybody, but there's something basically wrong, I think, in that. You know, it reminds me when in the 30s, 100 German scientists wrote a letter proving, quote unquote, that Einstein is wrong. And Einstein said, why 100? If I were wrong, one would be sufficient. Okay, one of the consequences, I'm almost finished, so don't panic. One of the consequences of inflation is something called universe, also the string theory. They should be, it's our universe, and there should be almost infinity, or maybe infinite number of other universes, totally disjoint from ours, inaccessible to anything. But there are papers, people are calculating the probability of having our constant in universe. It is something which is, it's no longer science, at least I think, and also my friend and great physicist George Ellis wrote that the multiverse idea is not provable either by observation or as an implication of well-established physics. It may be true, but cannot be shown to be true by observation and experiment. It's no longer physics. But if you think that everybody would agree with the same statement, you are mistaken. So let's say, made the proposition that the theory cannot be tested experimentally and or observationally. Is it a science? There's now something which is called post-experimental science point of view. I like the word post-experimental. Before post-experimental, when you finish the experiment, and now post-experimental is the science is post-experimental. And it says that if the theory is sufficiently elegant and explanatory, it need not be tested experimentally. And the adherents are some philosophers. The main philosopher is Richard, because he's German, Richard David. There are many stringers, of course, and multiverse cosmologists, of course. There are some question, who decides what is sufficiently elegant? Or what is the meaning of explanatory? If the explanatory, yeah, in a mathematical sense, something may be explanatory, but if you don't test it, so it is the beauty that decides. But are going to be myths of superstrings, or you know, and you know, even with myths of the encounters, there are separate juries now. I think in France there are two juries, you know, fighting each other about who is going to be a terror and a Politburo. Of course, we knew there was the Lysenko's apples were much or Michourine apples were much better than Vavilov's apples, and Vavilov finished dying of hunger in a concentration camp. Of course, I'm exaggerating. Nobody will going to put into prison somebody who finds that the theory is not beautiful or sufficiently elegant. But I don't know where it leads us. And this is not new. Of course, if you read this quotation, this was also sociologists of science, and they claim that physics is just, a conversation between physicists, and there are all these ridiculous statements. The natural world has a small or non-existent role in the construction of scientific knowledge. So it's not new. There's also this fantastic citation much later by Professor Catherine Hales, who claims that the conservation laws are not conservation laws, it's a conspiracy by men. She didn't say white men, but men. I mean, this shows the ignorance of such people, because the conservation law, just the example which is chosen, is completely ridiculous, because all the conservation laws are based on so-called Netter theorem. Netter is the name of Emmy Netter, a great German mathematician, Emmy Netter. She was certainly not a man, even if she was white, but that is another story. So what is new is not these ridiculous things, but what is new that some physicists provide support for such outlandish views. This is new. And this is dangerous, I think. I'm not the only one to think that, but, I'm who I am to protest 6 or 7 Nobel Prize winners, or even if they're good friends sometimes. So I want to finish by a statement and 2 quotation, that if physics were to become post-experimental, this would not be only the end of physics as we knew it, but simply the end of physics. Fortunately, physics is not only superstring and multiverse, as I've shown you before. And then a very well-known quotation from Ludwig Boltzmann, one of the greatest physicists in history: if you are to describe the truth, leave elegance to tailors. Einstein liked to quote it, but he was also adding shoemakers for some reason. And this is the point of view that I think we should stick with, expressed in Ethic of Nature by George Ellis and Joe Silk. In our view, the issue boils down to clarifying one question: what potential observational and experimental evidence is there would persuade you that the theory is wrong and lead to abandoning it? If there is none, this is no scientific theory. This is a version, of course, of a well-known criterion of falsibility and falsifiability, and I think we should stick to that. But many people say that it is obsolete, and this is a danger. I hope that reason will win, but by nature, I'm pessimistic. Thank you very much.
So we have a little bit of time for questions, and I think we have...
No, as I said, I'm hard of hearing, so
right.
I may have problem. No, but with some help, I will...
If you could yell vigorously,
yeah.
And then I'll yell vigorously again, and we'll be rather convinced.
Just don't be surprised if I...
Thank you. I enjoyed that talk, and I'm a former physicist. Of course, CERN now proclaims it's the birthplace of the internet, so there was a spin-off, and I think governments will still be funding particle physics a little longer. I want to make a comment about James Webb. The James Webb Space Telescope, it is a dramatic case of overspend, but it's also perhaps a very unique case because they're terrified, because if they can't repair the telescope in orbit. So it might be, although I think you're correct in what you say about overspend, it is perhaps a little bit of a special case. I think right now they're just terrified of launching it because if anything goes wrong, they throw away $10 billion. I think that's a big problem. But my question was about string theory. String theory, you said it's not testable. There was one prediction made by string theory about 20 years ago that the universe, the rate of expansion of the universe might be slowing down or might just be stable, but they said it could never be accelerating. And then there was an experimental measurement, which experimentally the universe does appear to be accelerating. So, what's your? I get the impression that you're a bit skeptical about string theory. Would you like to say a little bit more about the current status of string theory, as it's still so popular among the theoreticians? The popularity of string theory, is it justified?
Yeah, was perfect. I will answer. I will. Of course, the GWST is special, but unfortunately, it's special because of the scale. But I've been involved in several European experiment and project, and I don't know if it's a single one that was not late by 30 to 50% time, was not overspent, not by such a huge factors. And I think you are right. This is a very complicated project. They were unlucky with various phases, but I think it is a general feature of this big science that I'm retired, but I'm still saying we don't know how to run them. It is the same thing with military projects. It is the same thing with planes, as we have the best example with this Boeing, etc. It's a general problem. We don't know how to run big projects, and I think the main reason is that people are afraid of responsibility. This is probably so that you always want to have a committee to decide, etc. People are afraid of the risk, and in the end, you risk much more than, but it's not personal because the responsibility is spread. I'm maybe cruel about it. Now, the string theory, the problem I think with superstring theory is that it can make many predictions. This is what was this was also the argument against inflation. This type of very speculative theory, they have so many elements you can adjust when you get an observation or an experimental result that contradicts you. I don't think, I'm not an expert in string theory, but I don't think you could say that the string theory predicted that the universe will be non-accelerating or even decelerating. I don't think there's an equation that can deduce from the string theory to prove that. This was an argument that probably, I don't remember now this argument, that probably in the sixth dimension you found a solution that is dual to something that it is how it works. It never makes definite precise prediction like Maxwell said, electromagnetic waves exist. If you do that with the electrons, you will emit an electromagnetic wave. This is not such a prediction, and I think this is the problem. This is what the last sentence said. I think you cannot put string theory in the category that would satisfy. Oops, sorry. Oh no. This is an invention by that would put in this category. Of course it's not. It's more general. It's not. It doesn't. The testing physical theory doesn't work. You make a prediction. All swans are white, and then you find a black swan. Also, my theory doesn't work. You can. Many times you see, because this assumption has to be changed, etc. But I don't think that string theory makes this type of prediction. On the other hand, it is very popular because I think among young people, because it's very attractive, it's beautiful, it's mathematically beautiful. I wish it were true, because the argument is, and I understand this argument, the argument of people who say it is so perfect as a theory, and it makes all these predictions, they are internal predictions. And you find this new thing. There was this time when there were 6 different string theories, and it was an argument against how can you give it 6. And then it was found it's only 1, that there are some limits, and it's so beautiful. They talk about revolutions in the strings. They understood, they incorporated gravity, all that. It is mathematically beautiful, but beauty is not a proof. The steady state model of the universe was beautiful, and it was solving the problem of the Big Bang, of the beginning of the universe, which physically was found outrageous by Eddington, by Einstein, and etc. It was beautiful and self-consistent, but it was wrong. And and there are some other examples of beautiful theories, or even useful theory. I showed the Carnot cycle. Carnot discovered the law of thermodynamics by using the wrong theory. He was using the caloric theory. There was supposed to be a substance, it was called caloric, that doesn't exist, and but so you can even wrong theories can be useful. But in the end, they must be testable, and caloric didn't pass the test. So I don't know. It's maybe, you see, the worst would be if this superstring theory is the right theory, but we cannot prove it. So we'll be stuck forever. On the other hand, it is a superstring theory, and so it requires the existence of supersymmetry. Supersymmetric particles. They are still to be found. I think if we arrive to some energy rather high and there are no trace of supersymmetric particles, you can always say yes, but maybe let's build another accelerator and see. But I think it will become less popular. But I am a great admirer of the string theory. So I don't know why I was talking to that, because I have this here, but I hope it didn't.
Thank you. Professor Lasota, I have a question for you. Do you think mathematics is something that exists in the world, or do we bring mathematics into the world? Because I noticed that you use terms such as mathematical beauty, and when I think about a number, I really don't see if one number is more beautiful than the other. And it brings me to another point, which is you talk about measurement a lot and the precision of measurement. We quote, know everything. But it seems to me that at some point in your lecture, there's a difference in what are the classical measurements and what are measurements in the realm of mathematics that are inferring to rules and axioms. And that sort of brings us back to the end of the lecture where you talk about computation, because the world of computation is limited by the world of classical mechanics. And so it seems that you are doing the type of physics in the realm of atemporal maths premised on infinity that requires a level of computation that we don't seem to have, even if you think quantum computing is something that's possible or not.
Yeah, that's a very good point. And it's a deep philosophical point, and many people wrote about it, and Eugene Wigner wrote this famous article about the miracle of mathematics fitting so well to the real world, and it is a miracle. I'm sorry, I don't mean miracle in a sort of not literal sense. I am not going to theological things. It is, we don't really understand. And of course there are some visions of I think Roger Penrose, like this correspondence between the Platonic world, let's just call it. But this is all a vision of the things that in practice, the difference between the mathematical world, as you mentioned, and the physical world, that the mathematical world is perfect. If you have a Euclidean geometry, you measure the sum of angles in a triangle. It is always 180 degrees or 2 pi to infinite precision, because it is mathematics. In the real world, and since we don't believe anymore in what Kant believed, because Kant believed it is also true for the real world, but we know it's not. If you measure the sum of the angles of a triangle and you get 180, it will be plus minus something. It will be never, you can never believe that you got, there's no way, because this is the real world. You apply the mathematics to that, but you are not in the Platonic world, it is in the real world, and you can always expect geometry, which is the basic mathematics. You can always expect that at some level there will be a difference between the result you expect from Euclidean geometry and, in fact, we just observed what I've shown, what are gravitational waves, are exactly that. They are extremely tiny differences from the Euclidean geometry. And so it is, when we increase the precision, we found the discrepancies, which we'll never find in the real mathematical world. But if you are sure, you have to check if they are due to the nature of what you are studying or to your measurement, and this is very difficult to know. And this was the best example of the Hubble constant. But if we found that the Hubble constant was different at the beginning of the universe, I mean, that the Hubble constant deduced from the physics at the beginning of the universe compared to the present measurements of the Hubble constant are different, then it will be a sign that there's quote-unquote new physics. There's something new was happening. And this is why we are doing physics I mean, not everybody, but many people do physics to find that something is wrong or that they were wrong. And you cannot do it mathematics like that. You cannot do mathematics trying to convince yourself that you are wrong, because it makes no sense. Whether in physics, it always makes sense, to a limit, of course.
We really have time, but I think we've got so many questions. I'll take one more, one swift question. Jonathan.
Would you like to? No, go on. I have a technical question which I will discuss in private.
I'm curious.
Not a difficult question.
I want to know if you think what you think the role for elegance or beauty might be. We've understood the criticism, but many of us operate in a classical epistemology where we, at some point, believe that beauty, truth, and goodness will be reconciled or could be reconcilable. Could you just answer what you think the use of beauty or elegance might be for physics?
Yeah, I mean, this is it's an easy question and a difficult question at the same time, because I would say, you know, all this beauty, let's forget about it. It has no place in when you do measurements. You have, you know, you are doing physics is dirty, okay, and so don't look for beauty. You would say the opposite is dirty, so look for beauty. I would say that, but great physicists, Paul Dirac, for example, he was, it is incredible, but he said, of course, he was a bit special, but he was a bit like Feynman, but not in the same way, but he liked to be provocative. But he said for him, the main criterion is beauty, beauty of the equation, beauty of the reasoning. So I cannot say, you know, forget, you know, this idiot Dirac, because I am an idiot compared to Dirac. But I don't think it can be recommended as a general attitude to physics. If you are Dirac, you know, if you are Dirac and no, the most funny thing is that if you believe Dirac, and then you won't do it, but if you look at the Dirac equation, which is incredible, you can't believe that a human being was able to find such an equation. But beautiful? It's not beautiful. It is fantastic. It is incredible. You know, but it's not beautiful. But to Dirac, it was beautiful. You know, and the beauty of the equation is depends how you write it. You know, you can write the Einstein equation in a beautiful way. Okay, G equal 8 pi t. It is beautifully simple. But if you write them really, if you want to solve them, they are horrible. They are horrible. Many people gave up. You know, now we have computers. So beauty, in the sense, you know, you can say beauty of a person, beauty of a is also subjective. But it's like you watch this young girl with the red necklace. You know what I'm talking about. He doesn't. I know. Okay, I will show you. You don't know? You've heard of Human Philosophy Project?
Oh, yes, our LIGO, yes.
You see, okay, you see it, and tomorrow it will be the same. You can make it, of course. You can decompose it, and it's very fashionable, but it won't be the same. If we find this beautiful, it is beautiful. An equation. It is only if you create this equation, like Dirac created this equation, he said, "Oh, this is really beautiful." But it is what's creation? It's like your child is beautiful, even if not your child. I mean, but if somebody's child, you know, he said, "It's the most beautiful in the world." Others says, "What is this?" This is, you know, Dirac equations like that. So I don't think beauty can be applied to things that, you know, and the Newton equations are supposed to be very simple. Okay, but my physics supervisor, Ajay Trautman, decided to show that you can write Newton's equation in the same formalism of differential geometry as you write Einstein equation. It becomes horrible. It's still the same equation, become horrible. So beauty, no, I don't think I am for beauty, but not in physics.
Well, I think you get a special...
No. I just wanted to remind you that you did not answer the first part of the previous question, which is very important, and I'm sure everybody wants to know. Do you believe mathematics exists?
Sorry, could you speak up?
Mathematics exists, and do you believe numbers exist? That was
Oh,
the beginning.
I know, but no, okay, this is, but you know, I have an opinion, but is it interesting? If you entered my opinion, I'm very honored. I think they do exist. Of course they do exist. They must exist. I don't think you, when you find a theorem, you discover a theorem. I don't see how, but you know, it's just my private view. I'm not a mathematician, but I share Roger Penrose's view that, because I think unless he's changed his mind, but he claimed that, no, I think that maybe it's my weakness, but I cannot imagine that they could not exist. Because if they don't exist, what, you create them?
Well, the question is, do they
It's but you,
from your experience of reality? Are they sitting somewhere in abstract space?
yeah, this is where are they? They are in a, okay, but it's a good place, you know, this, to speak about things that are not physical. You know, it's I can admit here that I don't think that all reality is physical in the sense that you can say it is there or it's, but it's complicated. That's why I'm not a mathematician.
Well, on that note, I'd like to invite you all to join us with finishing the wine and nibbles. But before we do, if you could join me in thanking Jean-Pierre.